Hello and welcome back to today's AutoML lecture series. Today we will talk about DARTS, differentiable architecture search. So in the last lecture we talked about one-shot models, and that one-shot models remove the need to retrain individual architectures. However, the search over the subgraphs is still discrete, for example using Bayesian optimization or evolutionary algorithms. However, this discrete search prevents us from using gradient descent approaches, or in general gradient descent, which is kind of the powerful optimization tool in deep learning which we use on a daily basis. Therefore, the idea of today's lecture and also the approach DARTS which we will talk about today is to relax discrete operation choices to continuous weights so that architectures become differentiable with respect to a loss. So therefore, the key question we want to answer today is, can we formulate NAS as a gradient-based optimization problem, optimizing over architecture parameters and network weights jointly? So, DARTS, differentiable architecture search, was introduced by Liu et al. In year 2019 and is one of the most popular approaches for NAS with one of the most cited papers so far. The idea here is based on a one-shot model to phrase it via a continuous relaxation of the discrete architecture search space in order to allow gradient descent. So as we can see here in this overall figure of DARTS, on this side here we can see that we have again a cell-based search space, so therefore DARTS can be used for any directed acyclic graph or cell-based search space where the operational choices are on the edges, connecting again two nodes with each other, tensors, and therefore resulting in feature maps, and also being then stacked n times. So let's dig deep. At the very beginning we have our edge ej, for example here, which connects node I to node j, which contains multiple candidate operations O, here also visualized in 4 different colors, therefore 4 different operational choices. And each of these choices is associated with a continuous parameter alpha. So at the very beginning, we could say we have 4 different operational choices. So each of these choices gets a 1/4 more or less weight of being applied towards our input on our input node xi when we have an edge I to j. So if we look now at our tensor xj, we have that the tensor is computed as a weighted sum over the predecessor's node of j being I, so here the predecessor node xi, which is then calculated with an operator O tilde, which goes from node I to node j applied to this previous node xi. And this operator exactly is kind of the mix of all the candidate operations. So what does it actually mean? We train our super network, and our edge eij, so going from node I to node j, from xi to xj, consists of the mix of all candidate operations. So here a mixture of 4 different operations, and each of this operation is applied to xi and then multiplied by a softmax of alphas. So therefore we multiply each individual operation applied to this input node xi with the strength of the individual operator. So very loosely speaking, kind of a distribution of the weighting of the different operations. And then we sum it all up over all the predecessors. So we can see here over all the predecessors of j being I, since we have not only one node being connected to node j, for example, but several nodes. So, and then the operator weighting operator weighting is done by alpha for each predecessors. So the alphas allow us to learn the architectural part, so of which operation on which edge gets kind of the largest weight being applied to the input of xi. These alphas are not a discrete. They are not 1, they are not 0, and we want to learn them via gradient descent. However, in order to get a single architecture, which is kind of our overall goal, we need to discretize this continuous relaxation. And at the very last step, we also do some retraining from scratch. So in order to actually get the discrete architecture and the discretization, we just select the operation with the maximum value of alpha on each edge, ij, which is kind of the discretization step, which we can see here. So we can see that it's kind of the argmax of the alphas. And then we retrain the one network, which is discretized from scratch. However, this discretization is simple, since it just like takes the maximum value, but it can be very brittle, since we actually learn our super network using a continuous relaxation between the different operations, which are then eventually discretized and thus can lead to several failure cases, which we'll also talk about later. So let's look now at the actual optimization. So in order to go from an initial state to this optimized state, DARTS solves the so-called bi-level optimization problem. So looking for architectural weights alpha, such that if you set the weights of this also in a way that they minimize the training loss. So if you optimize the weights for this particular architecture with respect to the training loss here, so you have an architecture, you want to minimize the training loss in order to optimize for the overall weights. You also want a minimized validation loss. So we have here our outer level, which is kind of the architectural error, optimizing the architecture given that you have the right weights for this already, and optimizing also eventually with respect to the validation loss in order to generalize. So that's kind of the outer part. And then you have the inner level, which evaluates for the training loss, given that you have kind of more or less already an optimized alpha. And so how do we actually optimize it? We just use alternating stochastic gradient descent on the architectural parameters alpha as well as on the weights W. So we optimize, for example, the weights by looking at the gradients of the training loss, which is the inner level, with respect to W, and then update the architectural parameter by looking at the gradients for the validation loss with respect to alpha. And we iterate that until the time is up. Very important here is that there is no theory showing that this process actually converges. All the evidence is purely empirical. And now let's look a little bit more into how DARTS actually is defined, or more or less what search space is defined, which is also sometimes used as loosely speaking as the DARTS search space. So the search space itself is defined by having 8 operations connecting 2 nodes with each other, and therefore having in total 28 edges. So it's a fairly complex space and eventually leads to more than 10 to the power of 23 different possible architectures. And what it's also doing, it does not only search for one cell, which we have seen, for example, in one-shot NAS or different search spaces. It searches and optimizes for 2 different types of cell, a normal cell as well as rejection cell. And the actual results of DARTS on Cypher 10, for example, for image classification can be seen here. So we have here our normal cell, which is learned on Cypher 10 image classification task. And we can see that we have mostly some separable convolution, like 3x3 convolution. We have some dilated convolution and also some skip connection in order to not let the cell become too big. And then we have a reduction cell, which reduces the spatial resolution, which is mostly defined by skip connections as well as pooling operations. And what is kind of nice is that these 2 cells which were found using DARTS lead to an error less than 3% on Cypher 10 in less than 1 GPU day of only search. However, the issue is that DARTS is not really robust. It does not have a really robust behavior, and it's very sensitive with respect to its own hyperparameters. For example, the one-shot learning rate, the L2 regularization, starting that we have 2 different learning rates for the alphas as well as for the weights of the operations, as well as 2 different regularizations, 2 different optimizers, all these things. And if you don't tune the hyperparameters, the overall approach can become very, very brittle. So you need to tune these hyperparameters for each new task and search space, which is exponentially very expensive. And if we don't tune the search space, one example can be seen here, that DARTS completely then degenerates the architectures and creates a cell, or searches and finds a cell which mostly is composed of skip connections. So that's one of the issues which DARTS has. So in order to overcome this issue of kind of moving towards degenerated architectures of only finding skip connections, there are two approaches which we will talk about briefly now. One of them is robust DARTS from Arbeit Zähler from 2022 from the University of Freiburg groups, which tracks the curvature of the validation loss and stops the search early based on that. So what is happening is that if we look at the largest eigenvalue of the Hessian matrix of the validation loss, this will kind of give us insights into how steep or flat the computed weights are. And that is exactly what they plot here. So we have here the amount of search epochs, and we can see here the validation error. We can see that actually over the search, the validation error decreases. So the optimization itself is not an issue. But if we look also at the test error, which is plotted here in this part over the search, we can see that it starts kind of highish, goes down, and then moves up at some point. And if we now look at the dominant eigenvalue, so exactly looking at the curvature and how steep our optimization areas are, we can see that it actually also increases in the same more or less behavior as the test error is increasing. So we can see actually that the curvature rises and therefore also the test error rises. This is happening somehow in the same epochs areas. And DARTS performs actually poorly when the architectural eigenvalues get too large. As we can see here, the larger the eigenvalue get, and thus the more and the sharper the minimum is. Therefore, that's why they look at the curvature. So in order to stay in a kind of rather flat minimum, they just like stop when we have a rather low minimum, have a rather small dominant eigenvalue, to not get into kind of a very steep minimum. And one reason why that is actually happening is that the discretization, in order to get the actual discrete neural network from continuous alpha, actually means that we prune the architecture in order to obtain this discrete network. But it actually kind of looks into the neighborhood of the actual optimized alpha. And depending on how close or how far the optimized alpha from the discrete version is, the further we go away from the actual optimum. So if we have a rather sharp minimum more or less, and we have our optimal alpha here and our discrete version is up here, then the minimum is the optimum is actually not close to the actual optimum of the chosen alpha. So therefore, that is kind of the idea of why they want to look at the curvature. Similar, rather than training and optimizing for the training loss, there is also smooth DARTS, which kind of has the same idea of what happens in order to looking at the minimum more or less. Also, they have seen that the issue is kind of the flat and sharp minima. So what they do is they optimize the expected or the worst case training loss over a local neighborhood of the architectural hyperparameters. So the idea here is to have more smooth behavior with respect to any kind of perturbations. So if you have a very sharp minimum again, or a sharp optimum having some perturbation, then you go very far from the actual minimum. In order to make it more smooth, they just like include random perturbation already into the training, or apply at the serial training that is happening. This is similar to what we would do in images as well. So another idea or another issue with DARTS is the memory constraints. So DARTS keeps kind of the entire one-shot model in memory together with its computed tensors. And this constrains the overall search space size and the fidelity used to train the one-shot model. Therefore, it's impossible to run on large data sets such as ImageNet. So for example, on Cypher 10, what the DARTS paper is doing is they search for 8 cells, and the retrained version then contains 20 different cells. Since the memory requires to train a supernet is much higher than just like training a complete normal network. So if you say I have a neural network which fits on my memory that we can train on ImageNet, using that as a super network is just like impossible here anymore. Since it scales linearly with the size of the set of candidate operations. So if you have 4 different operation set, you have 4 times the memory needed to actually fit your network or the super network actually in memory. So there's a lot of research done in order to fix this memory issue, and one of the examples I want to mention now is the GDAS approach, which samples from a Gumbel softmax, or it's so-called Gumbel softmax, to keep only a single architecture memory. So what's happening is that we have kind of a Gumbel softmax distribution over a one-hot encoding of the operational choices, and therefore we just like select one of those operational choices every time differently in order to allow for sampling in general and overall. Single operation in each training step, while maintaining the differentiability, since we have kind of a softmax distribution happening here, and therefore we only have kind of a single architecture in memory, so therefore only looking at one single architecture at each batch, therefore the memory is not an issue anymore. Another work which I want to mention is proxyless NAS, where the overall idea is to keep only 2 or also 1 edge between the nodes in memory. And these edges are kind of chosen randomly based on the probability proportional to the current value alpha. So therefore, we have 1 path or 2 paths of the activation which is active in memory at runtime, and therefore the memory requirements are also not here an issue anymore during training of the overparameterized network. So therefore, this would reduce the overall memory to the same level of training one compact model or having slightly more memory if we would keep 2 edges in. And the last paper I want to mention is PC DARTS, which proposes a relatively simple approach at each training step and for each edge in the directed acyclic graph. Just a subset of the channels is sampled and sent through the possible operations, and while the remaining channels are directly passed towards the output. So in general, what we talked about is DARTS, differentiable architecture search, which uses a continuous architectural weights alpha to make the search differentiable and can be optimized during using gradient descent. We use a bi-level optimization approach in order to go from the initial state to an optimized architecture, which alternates between updating the weights W and the architectural parameters alpha. And the issues with DARTS is, though being very efficient, it's very sensitive to hyperparameters and may produce degenerate architectures, as well as memory issues, which we just mentioned on the last slide. So thank you very much for listening, and hope to see you again in the next video.